Okay, so we derived an equation for the disk, which reads 1 over eta, well, eta is, it involves the magnetic permeability and the conductivity, so it's that object. Faraday tensor, and the four velocity one form, so lowered, right? And we actually want to write the equations in terms of the vector potential, so it looks like that, and in particular because one of these components is the magnetic flux. So, and that result, so we're going to end up trying to understand the BZ power, the Blanford-Znaeck power, and that requires this flux on the black hole, let's call it psi, which from Stokes' theorem is, let's just write it directly. We won't derive this result. It's 2 pi times the a phi component of the vector potential. Right, so it's the third component in these coordinates, a3, which is a phi. We have some technical quantities, right? We have the gauge, which we have to specify, AB plus grad B of some quantity. But we are in a situation where we assume time independence and axisymmetry, so we end up with B, so if we're doing T prime is equal to AT, and a phi prime is just equal to a phi. So this doesn't really affect anything. So we don't need to specify this beyond saying that it's time independent and axisymmetric. And this reduces to an equation. So right, we know how to evaluate this in terms of these quantities. Of course, here we have the upper components, here we have the lower components. So we're going to need the help of the metric to put these together, but it ends up giving us an equation when we explicitly write it out in 3 plus 1 form. So we get an equation that looks like, right, we have derivatives in here, and so we end up getting derivatives in R, G11, we get G30, we just want to write it out to get a sense of the differential equation that we get. In dt r, that's the A0, if you will. I wrote it as T, plus G33, the derivative of the flux, A phi, or A3, right, with respect to R. That's the magnetic flux, plus d by d theta, metric components, G30 dAt by d theta plus G33 dA phi by d theta actually. Plus we have a 1/2, let's see, G00, the radial derivative, the G00 metric component, plus 2G30 dG30 in R plus G33 dG33 in R plus G11 dG11 in R plus G22 dG22 lower in R. All this times, well, this gets multiplied by G11, but it also gets multiplied by G30 dAt in R plus G33 dA phi, our flux function, which is what we want, dr, plus 1/2 G00, just to give a sense that we ultimately end up with the differential equation for the quantity we're looking for, the magnetic flux, plus 2G30 dG. We can kind of see a pattern here with respect to theta, plus G33, and the derivative of the lowered component with respect to theta, plus G11 dG11 with respect to theta, plus G22 dG22 with respect to theta. That gets multiplied by G22, and we have here G30 dAt in theta plus G33 dA phi in theta. And that's the left-hand side. That's this thing. And so the right-hand side ends up being 1 over eta UR, right? U, the radial, G11, G30 dAt in R plus G33 dA phi with respect to R. So that's what this thing reduces to, and the differential equation will simplify it further.